This is a production of Cornell University.
Okay, so the factors are those variables that change across the landscape that are the architecture or the basis for what the soils or from which the soils are made, how they're made from, and what they're made from. Okay? So you were out there this week, and we basically talked about two parent materials. Okay, and I'm going to sort of go through all the soil forming factors. Okay, so what were the parent materials that were there? We've got a sand deposit. It's coming as a stream deposit off of the glacier. That's your first parent material. The second parent material was this loess deposit that was put on top of it. Okay? Now, how they got there is important, but from the soil's perspective, how it is formed, what's important is how it's arranged in that space and what it is. Does that make sense? Okay? How it's arranged in space, good example there is the stratification of the sands. Okay? That sand as a stream delta was not dumped as a bucket. It was dumped year after year after year in strata laid by each of the floods. Does that make sense? Then we had a loess event afterwards. Okay? The wind particularly, it selectively picked up the silt and rearranged it across the landscape. There was silt in that deposit prior to the loess deposit, but the wind blew through. It basically selectively picked up the silt across the entire landscape and then redistributed it by putting it on the top. Okay? The silt came from the landscape, and then it just got picked up and redeposited. So we basically had an accumulation, or actually I should say first, we had a selective loss of silt in this material that was there, and then we had a selective addition of silt on the top. Does that make sense? Okay. Then what happened? Well, we had climate on top of that. Okay? Temperature and moisture. It took that silt cap and basically started to weather it away, producing smaller particles that became clay, clay-sized. Those clay, because of the moisture, the rainfall that's around here, the clay moved through the profile and was deposited farther down, alluviated farther down. And that was where those BTs were formed. Seems straightforward? All of that story basically comes from where I'm creating it, in essence, basically out of the soil forming factors. And I will be talking about the soil forming processes, and a lot of that story is basically additions, losses, translocations, transformations, and those are the processes. And you'll be introduced to those today. Okay, questions? Do we feel good about, I mean, did I'm not a good answer. Okay, so where we stopped was was right here. Okay, so about parent material, we talked about climate, and we talked about biota. So let's start talking about the soil forming factor of relief, or topography. Okay, where something is in the landscape and how it's arranged. Okay? So relief basically can determine the effective amount of precipitation as well as soil destruction. And the classic example that they show is this one right here. Okay? So if I have a profile, these are three different profiles at three different points in the landscape. One is at the summit, one's on the sort of the shoulder back slope, and one's at the foot. Okay? Each one of these has a different profile. So this is an A horizon, E horizon, a B, a C. This is an A, B, C, and this is a very deep A with a B and a C. Okay. Explanation. Why do we have this profile here versus here versus here? Well, gravity happens, right? Imagine we have a rain event, okay? And it rains evenly across this entire landscape. Now, some of that rain is going to do what? It's going to infiltrate into the soil. Some of it's not, though, okay? The flatter the landscape, the more water I'm probably going to have infiltrate into the soil. Does that make sense? Okay, so at the top, I have a fairly flat landscape. Some of that water, or most of that water, or much of that water is going to infiltrate in to the soil. Not all of it, though. Some of it's going to start flowing downhill. Soils that are here, it rains here as well. Some of that water is going to infiltrate. But because of the slopes that are here, potentially more of that water is going to be overland flow and start moving down slope. Ultimately, we're going to get to the bottom of this hill. It's going to be raining just as much as it is up there. So I'm going to get all that delivery of water, but I'm also going to be getting the delivery of water that's flowing downhill. Which means, while my actual precipitation across this entire landscape is the same, my effective precipitation is a lot less up here than it is down here. And in fact, it's a lot less here than here. Well, why? Well, more of it's infiltrating here than here. Yes, more of it's being delivered this way, but most of that's basically going right through the system and being delivered down here. Now, if moisture is one of the soil forming factors, just by modifying my relief, I've modified moisture. And the response is, look at my horizons. Very different horizons. Up here, I have a moderately thick A. I also have an E horizon, which means the water's moving through and stripping stuff. Here, very thin A horizon, no E horizon, and a B horizon. Well, why? I'm not getting enough water to move through this system to potentially strip those E's. Yes, I still have a B horizon, but not much. This stuff comes down, nice thick A horizon. Well, why? I'm getting overland flow here, which means I'm getting a lot of erosion. I'm also seeing a lot of accumulation here. Where is it going? Those A's are getting really thick. Still have my B horizon, but I don't have an E. Thoughts as to why? I'm definitely getting infiltration in here. It's standing water. It's not getting leached. Why is it not getting leached? I got standing water here. The system isn't going through. It's perched there. Does that make sense to everybody? That's just the relief controlling something else, controlling another factor, in this case water. OK, that's the redirection of water. Let's use this second example down here. If you are in the northern latitudes, OK, this is north. This would be north. That's south. OK, we're in the northern latitudes. OK, we tend to find shallower soils on the northern sides of the slopes. OK, so here's my hill. OK, here's the sun. OK, deeper soils on the south, shallower soils on the north. The first and most obvious reason that you can think of here is that the C10 rule. You guys remember the C10 rule? As things get hotter, reaction rates increase. Okay? Well, if I'm in the northern latitude, the sun is shining more directly on the southern slopes than the northern slopes. The northern slopes are shadier. They're cooler. As a result, I'm getting more heat on this end, so I'm going to have more processing, more chemical reactions, which means I'm going to have more soil genesis, potentially leading to thicker soils. Now, this is not always the case, because if these soils are hotter, they're also going to be drier, which means I'm going to have wetter soils over here. Now, if I have wetter soils over here and drier soils over here, that's going to reflect two things. One is I'm going to have more moisture over here for chemical reactions to occur with, but I'm also going to have different biota communities, potentially. And if I have different plant species on this side than this side, those plants could be interacting with the soil differently. But in general, around here, the southern side of the slopes, the soils are deeper than on the northern side. Does that make sense? OK, I'm going to throw a couple sort of graphs at you, or not graphs, pictures at you, so you can sort of see some of this. First one's this. Out west. Can you guys see that slide fairly well? Looks great on this screen. Do you guys see we got a lake down here? We've got a sort of conal landscape here. We got a ridge coming out. The ridge is going around and it's creating sort of a bowl. Okay, where's the vegetation? Sort of in this zone. This is the confluence zone where if it rains in this bowl, where is all the water going to be concentrated? Straight down into this source area right here. I get more vegetation there, and certainly in the fall, I'm going to have more organic matter. Where do you guys think the deeper or the more developed soils are? Right in here. Does that make sense? Now, does anybody drive down 17? Going to the city or something like that every once in a while? Take the bus or drive down there? There's a series of these sort of concave or bowl-shaped valleys. And around here, it's a lot wetter than out west. And it turns out if you look at these sort of bowl-shaped valleys, this area is dominantly deciduous trees. And these areas are dominantly evergreens, just because of the shape of the relief. Now, in both cases, I've got plants, but I have very different plants. And one would expect that I have different types of soils because I have different types of plants. Does that make sense? Okay, it's most obvious when you're driving down there in the wintertime because the deciduous stuff has shed its leaves. But you'll see these bands. Questions? How about we throw this one in there? Now, I throw this in here because it directly juxtaposes this bottom slide here. Okay, in this case, we're not looking at the slope this way. We're looking at the slope this way. Okay, Baja. Farther south. Looking at that slide, which is the northern slope? This side or this side? Okay, so north is that way. Okay, because this is facing north. This is facing south. Does that make sense to everybody? In fact, that is correct. Now, I just said right here, if I got a southern-facing slope, I'm generally going to have deeper soils. This is a good example of where it's not the case. Why? It's wetter on this side. What else? If it's wetter on that side, what else am I getting in this scenario? Less direct sun, but what are all these things? I've got more vegetation in there, right? If I got more vegetation, the vegetation obviously is holding the soil, but the vegetation is also adding organic matter. So I have a direct addition. I've got organisms in there that are forming acids. They're basically building soil. This side, yes, there's some vegetation. Okay, so while I want you to keep this in mind, I want you to realize that some of these trends, there are very real things that happen on the landscape that can potentially change this trend. This is a generalization. You've got to always think about that specific site. And in this case, if you look at the site, it makes sense. Moisture, more organic matter, less stress on the plants. Yes, this side is hotter, but the benefit on this side is that I get more organic matter. Make sense? Questions? We good with this? The last one is time. And you guys have heard me say this before. I'm going to say it one more time. You give me a weak acid and 1,000,000 years, and I will weather away anything. Well, the same holds true. This is what time is all about. Okay? Soil formation rates are too slow for us to measure directly. Okay? But we can estimate the ages of material. We have a lot of different sort of tools. We can use carbon-14 dating. We can also look at historic events, and we can date it based on remnant materials, so volcanic ash layers. Or, in fact, we can look at datable artifacts. You know, we know that there was this thing here. There was a fire here, or a forest fire, or a building fire, or something like that. And then we can basically measure down to where that is. And we could say, OK, here's the ash line. I've got this much soil, and this ash line occurred here. It took me 100 years to get to here. Does that make sense? Or Krakatoa blew. Or we have cesium tests from the nuclear age. Okay, I can find that layer where the cesium is, and I can see how much accretion I have on top of it, and that's how much soil was developed in that period of time. Okay? The question comes, though, what in fact is time zero? Okay, let's go back to that cesium or the forest fire. Okay, I've got a layer in my soil of cesium. Okay, and then I have this much accretion above it. I can easily say that I grew my soil this much, or my soil developed this much in that time period, but there was a lot of soil before that. Does that make sense? Cesium is just a marker for that time spot, that time in the, that reference point. Time is very relative. At what point did this soil start? And then throw another added component on it. If any of these other four, if any other 5 soil forming factors, the other 4 changes sometime during that timeline, the development of my soil is going to change direction. Does that make sense? So I could have a soil that started as a sandbank and has been processing for thousands of years into one direction, and then all of a sudden something changed. A different organism moved in. A climate changed. The direction of my soil could totally change. Or it could totally stall. Or it could totally accelerate. That rate of generation can totally change based on these other factors. Does that make sense to everybody? Yeah? OK. Here's a graph that's right out of your book. And basically what we're looking at is time. And this is relative time, i.e. 0 time and how many years it takes to get to something. Now, this is just sort of conceptual. We don't actually, nobody's been around 100,000 years to have actually mapped this. Okay? But imagine we start with unweathered rock. Okay? The first 100 years or so, we're going to start seeing the evolution of an O horizon. Well, why? The first organisms that are moving into here are going to be plants. Okay? And they're going to start weathering away stuff. But most importantly, they're going to be dropping stuff. And that stuff is going to decompose, and I'm going to start developing an O horizon. Does that make sense? Okay. Well, as that stuff starts to decompose, someplace around here, I'm going to start producing a recognizable C horizon. Now, the production here, you got to remember, C is undifferentiated parent material. I'm not actually producing it, but I'm starting to see it because the rock material itself is just sort of wearing away. Okay? I'm also going to start producing an A horizon. If I have the mineral material, the mineral rock material that I'm seeing from the sea, that is going to start mixing with that O horizon through biological activity, and I'm going to have a horizon, the A horizon, a mineral horizon with the maximum amount of biological activity, maximum amount of organic material. Given time, we're going to start seeing those organic acids start to show up, and we're going to start seeing things move through these old C's and A horizons, and we're going to start seeing E horizons develop. The A horizons are going to start getting thicker, and we're going to start seeing some accumulation below. And those are those BWs. You guys remember the BWs? Weak color or structural development. The first sign of development in these B horizons. This horizon, this sort of younger material, this active material is going to get thicker and thicker and thicker. The C is going to get deeper. The R is going to be slowly weathered away. And we're going to start seeing more developed B horizons, more mature development. T's, accumulations of clays, accumulation of carbonates, oxides, colors, development of blocky structures as we get older. Ultimately, these soils are going to get really old, up to 100,000. That's not really old, actually. We're going to have very well developed O's and A's, fairly thick E's, thick B horizons, C's that are very deep, and the R's are basically out of the picture. Conceptually, that's the sort of the flow that we're expecting to see. Does that make sense? Go. OK, so let's take a look at some soils. And basically what I've done is there's a little bit farther. I haven't gone all. I mean, you can continue this quite some way, where you start losing B's and E's, and the E's disappear. But what I've done is I've sort of pseudo-replicated this transect with some real soils. Okay? So here's that fresh deposit. Now, this is not rock. This is basically sand. Okay? Fresh deposit, all the way up to the top, there's not really that big of a change. Okay? This would basically be considered C material. Okay? We're starting to see that C material here, but we're starting to see some formation up at the top. Now, this is agricultural land, so there's no O forming. But you can see the A up at the top, and you can see the beginnings of BW in here. Okay? A series of different C's, but you can see the lots of rocks, and it's starting to get some brown up at the top. A little bit farther along, we still have that A and that BW, but we're starting to see a zone here of loss, this E, with accumulations below. You see how those horizons are getting thicker and deeper. Okay? We continue this. Not much bigger than that. An A. E is farther up. The BW has sort of disappeared. BT, nice thick accumulation of the T horizon with the C farther down. Okay? Ultimately, you can start seeing these reds that are developing in here. These reds are those oxides. Okay? Ultimately, we're going to get to these really deep red horizons. These are the oxysoils. These are those old soils. We haven't talked about oxysoils yet, but we're talking about soils that have basically, all the mineralogy, all these rocks and everything that's in here have basically been weathered away and replaced with secondary minerals. And those secondary minerals happen to be rich in iron, and so as a result, they're red. Does that make sense? Sort of a gradual transect. Go. Why does the E move from below to further up? In this case, it's just an issue. First off, it's two different soils. But in this case, it's basically an issue of more weathering. Okay? That BW is slowly being stripped away as well, and it's being moved farther down. Okay? So down into this scenario. Does that make sense? So as a result, the E is moving up. Now, the reality is that E could be moving down. In fact, that E could be getting thicker. You know, I just happen to pick these pictures. There's no real causative reason why, other than age. Go.
So everywhere in the book, it generally depicts the soil profile going A, B, C.
Uh-huh.
But in reality, the E can be.
The E can be in a lot of different places as long but it's always going to be above a zone of accumulation. Okay. Even that example that I showed before, or I talked about before, where you have lateral flow. You're still having some accumulation below. Okay? The E there has to be some sort of evidence of this moving someplace. Go.
So how can there not be a B above a B if a B is the zone of accumulation?
How can there not be a B above a B?
An E above a B, like in the first one?
It depends on what that accumulation is. Okay? A B, when we say accumulation, it could be something that has developed in that place. And that's like a BW, where color and structure have developed in that location. Unlike this BT, where we're looking at a translocation of clays. Okay? Does that make sense? You can have a B without an E. You can't necessarily have an E without a B. Okay? And there's a couple of examples where you can, in fact, have that, but it usually has to do with some sort of destruction of something or other. Okay, whether it's man-made or otherwise. Does that make sense? Okay, go.
When I was in Africa, is this why most of the earth there is red because it's older? But then I understood that the older it is, the deeper the sea will be. But then there we would dig and it would hit rock after, I don't know, a foot.
A foot or so? Yeah, so the question is, I'm thinking, this, maybe correct me if I'm wrong, but the question is, when she was in Africa, she's basically looking at these soils develop, and if we're thinking about these soils, one would imagine that this material would get deeper and deeper and deeper and deeper as things weather away. Yet, they start digging and they find rocks fairly shallow. There'll be a couple questions. I mean, I don't know if you know the answer to this, but the questions are they truly rocks or are they concretions that are associated with this material? Or are they just rocks that are really resistant to weathering and everything else around it is big? Did you see these same colors?
I mean, it was red.
Pretty red? It might not have been, this is an oxysoil, but it could have been, there's ultisoils that a younger phase of this, sort of in between here and here, that there are still some rocks in some of these materials. You know, those rocks could have, I mean, a lot of potential explanations as to those rocks. What?
They're very porous and would break up easily.
Yeah, so that makes me think that these rocks are resistant to weathering. But after a couple 100,000 years, I mean, you can go down to Pennsylvania and you can basically have a rock and you can basically stick your finger in it and pull it out. You know, we call it saprolite. It's a rotten rock. It still has the shape of a rock, but basically the whole structure of that rock has been weathered away. And you can so if nobody's dug in this spot before, you can sort of see the artifact of where that rock was. Okay, and then you dig into it. It's sort of like did some of you guys see the fence post that we saw this week? Somebody had put a fence post in that Arkport soil. Okay, the fence had either been pulled out or had rotted away, but you could still see where that fence post was because things had filled in. Okay, it's the same sort of feature that's going to be happening here with this rock. In that case, the interior of that rock is basically rotted out. It's weathered away. And you got this sort of saprolitic rock. But if you could basically take your finger and punch it, or take your hands and just break it apart, that is indicative that that rock was from that location and it's just being weathered away. Just happened to have been a little bit more resistant than everything else. Do we feel good with this so far? Go. We haven't talked about that at this point, but the T, it's the BTs that you guys have met. Those are the accumulations of clays. The X is a fragipan, X, that dense, and you're going to meet those in about 3 weeks. The B here is probably it's been buried or something like that. Something has happened over time. Okay, these are a series of slides that are basically from University of Minnesota. And basically, we're looking at a spotosoil. Okay? This is a space-time substitution. Obviously, nobody's been around 10,000 years to have been able to take these pictures. But what they've done is they've taken pictures of spotosoils that are basically the same location, general location, and they've basically taken a look at different ages. Okay? Different ages of development. Okay? So here is 2,200 years ago-ish. Okay? And we're basically looking, you can see you can certainly see the O's and A's at the top. You can start seeing that A development, and you can start seeing some washes of red down here. Okay? You go to the other extreme, and you can see the full development 10,000 years ago. But you can see this progression. You can see how it started out pretty washed out. The E is definitely there. E, more development, more development, more development. You can see the reds filling in. And then you can see the reds filling in. And in this case, you can start seeing the organic acids coming in from above, stripping through, and really establishing that E horizon. That's basically that progression, 7,500 years. Does this make sense? I mean, it's pretty. I think it's a fairly good illustration of what we're talking about here. The processes start, weak expression, or fairly weak expression. Give it a couple more thousand years, pretty strong expression. Go.
Where do you go to get a successional band like this?
Around here, we'd probably go to the Adirondacks. I'm not sure where they went, probably in the 1,000 Lakes or 10,000 Lakes area. But basically, you can look at these soils. You can I find the same sort of features landscape-wise. I just try to date it. Okay, the reality is this could be the same age as that. This spot just happened to be more intense. Now they were able, and I'm not sure how they dated these, but they were able to date these. Maybe C14 or something like that.
This has been a production of Cornell University, on the web at cornell.edu.